Hello, my name is Jeremy Chu, and today I'll be discussing our paper WordGesture-GAN, Modeling Word Gesture Movement with Generative Adversarial Network. First, I would like to go over what word gesture typing is. Word gesture typing is a continuous stroke across a virtual keyboard in order to input an intended word. The video on the right depicts a user inputting a sentence using the word gesture typing keyboard. This method has been widely adopted on consumer virtual keyboards such as iOS keyboard, the Microsoft Swift keyboard, and Google's Gboard. In order to determine what the intended word is from a gesture, a decoder model is used, which combines a shape model and a language model to determine what is the likely word. Next, I would like to go over a word gesture production model, since that is what our model will be classified as. A word gesture production model simulates how word gestures are produced on a virtual keyboard. There are three key benefits to creating models such as these. These models help us to gain deeper insight into how users use a system. Second, they help to generalize how users interact with these systems. And third, these models allow us to create new unseen data that can help with the design and evaluation of interfaces. Here, I would like to briefly go over the basic structure of a generative adversarial network. In a generative adversarial network, two networks, the generator and the discriminator, are put into an adversarial minimax game. The generator attempts to generate data that looks as realistic as possible in order to fool the discriminator. In the case of word gesture production, that would mean creating as realistic of word gestures as possible, while the discriminator is attempting to discern the generated data from the real data. In the case of word gesture production, that would mean it is attempting to figure out whether or not a gesture is generated or real. Generally, for the discriminator, the output is a single value saying how real the input is. The generator generally draws from an easily sampled latent space, such as a Gaussian distribution, when generating outputs. However, with this simple setup, there isn't any way to control what the output of the network is. However, the addition of a conditional input can allow for the control of outputs from the generator. In our paper, we present WordGesture-GAN. WordGesture-GAN is a generative adversarial network that is able to generate word gestures. The model can use any arbitrary text as input and requires no reference gestures in order to generate a gesture. The diagram below shows a generalized view of how the entire network structure works. We summarize our contributions as follows. First, our model is able to generate full gestures for any arbitrary text. This includes spatially, that being the x and y coordinates of the points in the gesture, and temporally, that being the timing between the points in the gesture. Second, we use a variational autoencoder to control the latent space to ensure that it is easily sampleable. And third, we apply a 2-cycle training to ensure that the outputs have greater variety. Here, I will go over how a word prototype is constructed for input to the generator. The first step is to get the centroids on the target keyboard for the given word. After acquiring the centroids, we then perform linear interpolation between the centroids to construct the full prototype. These points are normalized into the range of -1 to 1 relative to the keyboard width and height in order to align with the output of the generator. We then add a time dimension, giving the time in seconds between the current and previous point, and the final resulting prototype is a sequence of points consisting of x coordinates, y coordinates, and the time between the current point and the previous point. Depicted here is a diagram of the generator structure. In training only, the variational encoder is used to encode user-drawn gestures into a Gaussian latent code. Like the variational autoencoder, the reparameterization trick is used to ensure that the output code is in a Gaussian distribution. This Gaussian latent code is then concatenated with the word prototype as input into the generator. The final output of the generator is then a simulated gesture. With the simulated gesture, That simulated gesture is fed into the variational encoder in order to generate another Gaussian latent code, which is used in the 2-cycle training to compare against the original latent code. An important part of training WordGesture-GAN is the 2-cycle training method inspired by BicycleGAN. Different Gaussian encodings Z should result in different gestures when input into the generator. At the same time, though, the encoder should be consistent in generating Z values from input gestures. In order to enforce this, we train in 2 cycles. The first cycle is to take a reference gesture, X, and input it into the variational encoder to get a Gaussian latent code Z. This Gaussian latent code Z is then input into the generator to generate a simulated gesture, and the 2 gestures, X and X prime, are compared against each other using a reconstruction loss. In a separate cycle, a random latent code Z is sampled from a Gaussian distribution and is input into the generator to generate a new gesture, X prime. This gesture is then fed back into the variational encoder to generate a new Gaussian latent code, and this Gaussian latent code is then compared against the original Gaussian noise by applying the L1 loss. Here we present some visual results comparing user-drawn gestures against WordGesture-GAN and 2 other word production models, the minimum jerk model and a style transfer GAN. Important to note is that the word voice was not seen in training for any of these models. Gestures generated by WordGesture-GAN resemble the way that users draw gestures for the same words. Here we present further visual results of generated gestures from WordGesture-GAN. To reiterate, none of these words were seen in training. As you can see from the bottom row, WordGesture-GAN is able to generate a variety of gestures for a given word. Here we present empirical results comparing the simulated gesture distribution and the user-drawn gesture distributions for each of the production models. The distance metric used is the Wasserstein distance, which can tell us the distance between the 2 distributions. The metrics used are the L2 distance and dynamic time warping. Important to note is in our calculation of the Wasserstein distance, the point order within each individual gesture is maintained. As shown in the results here, the WordGesture-GAN is more similar to the user-drawn gestures than either of the 2 other word gesture production models. WordGesture-GAN can also simulate the velocity and acceleration curves for gestures. In evaluating the correlation for velocity and acceleration against the user-drawn data, WordGesture-GAN is able to perform similarly to the minimum jerk model in predicting the velocity curve, and similarly to the style transfer GAN in predicting the acceleration curve. Since our model can also predict the duration of gestures, we also compare our model against the curves, lines, and corners model, or the CLC model, which is designed to predict the mean duration of gestures given a word. As can be seen from this bar graph, while the CLC model is able to better predict the duration of gestures for lengths of words that are shorter, as the length of words get longer, the WordGesture-GAN is better able to predict the duration of gestures compared to the CLC model. Since WordGesture-GAN can model the timing of points, this also means that we can play back the gestures in real time. The top gesture in blue is a gesture generated by WordGesture-GAN, while the lower gesture in orange is a user-drawn gesture. The WordGesture-GAN gesture has no reference to the user-drawn gesture. Here's another example for the word place. And here are examples of word gestures generated for various words from WordGesture-GAN. Thank you for watching. For more details on the implementation of WordGesture-GAN, please refer to the full paper.